Welcome back to Easy Tech. So the next test is Hopkinsons test. This is the most important question and this is repeated in so many times in an university's examination. This Hopkinsons test is also called as a regenerative test. A regenerative test or back-to-back test. Here is the motor and this one is generator, DC motor and DC generator, and the mechanical output of the motor is coupled to the input of the generator, and with the help of this prime mover, the generator will be rotated at a rated speed. It will generate the electricity. The voltage which is not sufficient to meet the losses, whatever the generator voltage is there, that is EG, as this one is EG, is not sufficient to drive this motor. That's why additional supply is required to meet the losses to start the motor. First of all, step number 1, start the motor with the help of a 3-point starter. But here 3-point starter is not mentioned. Start the motor with the help of a 3-point starter. After that, adjust the field rheostat of the motor to the rated speed, that is called the 1500 RPM. NS is equal to 120 F divided by P. Okay, this is the frequency of the back EMF. So once it will be rotating at rated speed, the generator is also rotating at rated speed. The generator produces a minimum voltage. EG produces a minimum voltage. By varying the field rheostat of the generator, adjust the field current. Yes, increase the field current. Field current increases, then the number of flux lines increases, and EG should be increases. Here I1 is called the supply current to the motor, that is called the line current. I1 is a line current of the motor. I4 is the field current of the DC motor, and here you can observe the current which is coming from this positive supply is I1. The current which is coming from output of the generator is I2. Now if you apply the KCL at this node, the current which is flowing through this line is called the I1 plus I2. In this I1 plus I2, I4 is divided, then apply KCL at this point. I1 plus I2 minus I4. This is the current which is flowing through armature. So once by varying this field rheostat, and if the generator voltage, the potential at this point and the potential at this point will be equal, the potential difference between these 2 points, let us say this is called the A and B, that means VA minus VB is equal to 0, then close the switch. The motor output is connected to the generator and generator output is connected to the motor. That's why it is called as a back-to-back connection. So this test is also called as a back-to-back test. A3 is the output current. A3 is the output current which is indicated by the generator, and A4 is the field current of generator. So these are the terms. V is the supply voltage. I1 is the current taken from the supply. I2 is the current taken by the supplied by generator. I3 is exciting current of generator. What is the I3 See, I3 is the exciting current, means the field current of the generator. I4 is the field current of motor. And what is the efficiency? The efficiency formula is output power divided by input power. So we can calculate the efficiency of generator and efficiency of motor also. What is the input to the motor? What is the input to the motor? So the motor is this combination is called the motor. The motor voltage is V. Yes, the motor voltage is E. The current which is flowing through the motor is I1 plus I2. Then the input to the motor is V into I1 plus I2. So neta is equal to output divided by input power, that is output power by input power. If you know the input power, output power is equal to neta into input, that is neta into V into I1 plus I2. So this is output of the motor. See, you can observe that output of the motor is given to the input of the generator. Yes, output of the generator. This is for the motor combination. This combination is for the motor. Output of the generator, again it is neta into input of the generator. As we discussed, the output of the motor, neta into V into I1 plus I2 is the input of the generator. You can observe that the motor output, yes, mechanical output is given to the mechanical input. So both shafts are coupled with the help of a mechanical coupling. So again neta, additional neta will be comes into picture. Neta into the input, you can substitute here neta into neta V into I1 plus I2. Then finally I got as neta square into V into I1 plus I2. So what is the output of the generator? The output of the generator is V into I2. So this entire combination, so whatever this entire combination, you can observe that the voltage is V2 and the current which is flowing through here, this one is I2. That is called the output of the generator. So output of the generator is V into I2, and the output of the generator in terms of efficiency is neta square V into I1 plus I2, and the output of generator from the diagram V into I2, both are equal, and neta square into V into I1 plus I2 is equal to V into I2. VV will be cancelled, and then neta square is equal to I2 divided by I1 plus I2, where neta is equal to I2 divided by I1 plus I2. So this is a full load test can be carried on two identical machines. So what is the armature copper loss? What is the armature copper loss? See here, the I3 current is divided. So always the current which is delivered from the armature, the I3 current is flowing through the field, and I2 current is flowing here. Then this current is called the I2 plus I3. If you apply the KCL at this node, the I3 is flowing in this direction, I2 is flowing in this direction. The current is I2 plus I3. Armature copper loss in a generator is I2 plus I3 whole square into Ra. Suppose if you want to find out the armature copper loss of a motor, so already I've marked the current directions, I1 plus I2 minus I4. This is the magnitude of the current which is flowing through the motor. I1 plus I2 minus I4 whole square into Ra. What is the copper loss in the shunt field winding? The copper loss in the shunt field winding is, see here I am applying a voltage is V, the V into I4. So but here you can observe that V into I3. So copper loss in field winding of generator is V into I3. Copper loss in field winding of motor is V into I4. And we can find out the total losses in a generator and motor equal to the power supplied by the mains. So one is connected to back. The power supplied from the line is called the V into S, that is called the V into I1, and the power drawn from the supply, but total losses in a generator and motor equal to power supplied by the mains. So power drawn from the supply is V into I2. We can find the stray losses. How we can calculate the stray losses? Input power is equal to output power plus losses, and there are two types of losses. One is constant losses, and one more thing is called the variable losses. We can treat that armature copper loss is a variable losses. In this constant losses, we have a stray losses plus shunt field copper loss plus variable losses. So constant losses can be stray losses plus shunt field copper losses. If you observe, from this we calculated the armature copper losses and shunt field copper losses. Yes, can I calculate the stray loss? If we know the input power and the output power. So the stray losses of both the machines is the power drawn from the supply is V into I2 minus, you can subtract all the losses, yes, I2 plus I3 square into RA, and I1 plus I2 minus I4 whole square into RA, and plus VI3 and plus VI4. From this power drawn from the supply, you can, that means input power, you can subtract all these terms, then I got the stray losses, that is called the WS. How many machines we are having? 2 machines we are having. So that's why for the stray losses for 2 machines are WS divided by 2. If the machine will be acts as a motor, you can find out the total losses. This is called the armature copper loss of a motor. This is called the shunt field copper loss, and this one is stray losses. Then shunt field copper loss plus stray losses, that should be equal to constant losses, and constant losses plus variable losses. Armature copper loss is also called as a variable losses. Then we can find the total losses. From the stray losses for both the machine is okay, and the total losses for a generator I have to calculate. Okay, these are the total losses for both the machines is WS, and this one is WS by 2. Then I found the for the total losses. Okay, total losses for a motor is I1 plus I2 minus I4 whole square into RA plus V into I4. Again it is a armature copper loss, that is called the variable loss, shunt field copper loss, and stray losses. You can observe that why we are taking output of the generator and input of the motor. So in order to find out the stray losses, if we find out the stray losses, then you can find the total losses. Armature copper losses is calculated by marking the current directions, and after that we found the shunt field copper losses, and shunt field copper losses and stray losses of each machine. Then you will get the total losses for motor and as well as the generator also. This is for the motor, I1 plus I2 minus I4 whole square into RA. Suppose if you go for the generator, so what is the armature copper loss? The armature copper loss for a generator, if you observe that I2 plus I3 whole square into RA. So I2 plus I3 whole square into RA. The remaining is V into I4 plus V into I3 plus W stray losses by 2. The output of the generator is V into I2. What is the output of the generator? V into I2. So that should be equal to output of the generator divided by V into I2, and the efficiency of generator is equal to output by output plus losses. The output power is V into I2. So output power plus losses of the generator, then calculate the efficiency of generator. If you go for the efficiency of motor, you can observe that the total losses we are calculated efficiency the motor. From the input of the motor we can subtract the total losses. Efficiency is equal to V into I1 plus I2. This is called the input of the motor. From this we are calculating the total losses of a motor. Total losses of a motor divided by input power V into I1 plus I2 multiplied with 100. What is the total losses of? So this is equation number 1. So you can write it as here equation number 1. Once again I am explaining clearly. See, this Hopkinson's test is also called as a regenerative test and or back-to-back test. So the motor output is connected to generator and the generator output is connected to the motor, and back-to-back we are connecting, and it will generate the electricity by coupling the motor to the generator. So the input current or line current is I1 and the field current is I2, and the current which is generated from the generator is I2 here. If you apply the KCL at this point, the current will be I1 plus I2, and this one is I4. The current which is divided as I1 plus I2 minus I4, and the current which is flows through the shunt field winding of a generator is I3, and here it is a current I2. The armature current is now I2 plus I3. So first of all, indicate all the currents and find out the armature copper loss after the shunt field copper losses. Then you can find out the stray losses. After that, stray losses for each machine also you can calculate. Then the total losses of a motor should be, you can calculate. If it is a motor, input power minus losses divided by input power. If it is a generator, output power divided by output power plus losses. So that is the value. The output power is V into I2. This V into I2 should be equal to the input of the motor. That's why the power drawn from the supply, I can take it as a V into I2. This test is also called as a back-to-back test. Thank you. So what are the advantages of Hopkinson's test? The various advantages of Hopkinson's test are, so the first one is the power required for conducting the test is small compared to full load powers of two machines. Yes, so it is required to meet the losses only. Already the motor is rotating at 1500 rpm. Yes, the motor is rotating 1500 rpm with the help of a field rheostat, and that is coupled to the generator, and the generator will generate the electricity. By varying this field rheostat of the generator, we are increasing the generated output voltage, and this small voltage or the supply voltage is required to meet the losses only. So that is the first advantage. Since the machines are operated at full load conditions, change in iron losses due to distortion and flux at full load will be included in the calculations. So if you go for the Simmons test, the armature reaction is not included. If you go for the brake test of a DC shunt motor or a DC compound motor or a DC series motor, at full load what will happen, and the most of the power is wasted in the form of heat, and also the armature reaction will be comes into picture. With that armature reaction, the flux will be distracted. That is not included in a Simmons test, and most of the power is wasted in the form of heat if you go for the brake test on DC shunt motor. So that is a disadvantage of the DC brake test on DC shunt motor. And coming to the Simmons test, we are not including the armature reaction. The exact efficiency we are not calculated. But in this machine, both the machines are operated at full load conditions. Whatever the iron loss which is distortion, the flux will be distorted, means maximum flux density is also changes. We know that hysteresis loss is directly proportional to, yes, hysteresis loss is directly proportional to B max power X, and the flux will be distorted, means and the maximum flux density is also changes. The maximum flux density is flux per area. As the machines are tested and the temperature rise and quality of computation of the two machines can be observed. Yes, thus test is economical as power required to conduct this test is very small, which is thus sufficient to meet the loss. Just now we discussed the same point only. There is no need for arranging the actual load. Similarly, by changing the field current of two machines, the load can be easily changed, and load test over complete range of load can be taken. So here we are actual load we are not applying on DC motor and as well as the DC generator, and by changing the field you can observe that the terminal points, the voltage at the top one across the switches should be equal to made equal to 0. Actually not loaded means that means we are not applying an external load, that is the meaning here. Anyway, we are output of the motor is coupled to the generator and generator output is coupled to the motor. And disadvantages is the various disadvantages of Hopkinson's test are there is a difficulty in availability of two identical machines, and the iron losses in two machines cannot be separated. We are assuming that the iron losses for both the machines are same, because the stray losses is a combination of iron losses plus magnetic losses. Stray losses is a combination of iron losses plus magnetic losses, and the magnetic losses for different machines will be different, right? But here we are calculating the stray losses for both the machines and divided by 2 we are taking, and the iron losses cannot be separated. The iron losses can be inbuilt of stray losses only. The iron losses are indifferent for both the machines because of different excitations, right? The machines are not loaded equally in case of small machines, which may lead to difficulty in analysis, and this test is better suitable in case of large machines. When you are going for the large machines, and this test is suitable. For small machines, this Hopkinson's test is not needed. And anyway, and this is the most important test, and this is the most repetitive question, Hopkinson's test. I think in your laboratories also you are doing this test, Hopkinson's test. Why we are going for the testing? We already discussed so many times. We need to find out the losses and efficiency of generator and efficiency of motor. Okay, if the efficiency of generator or efficiency of motor is good, then the performance is good. Okay.